Well, thank you very much for the gracious invitation to come by and visit and talk about some work I've been involved with for the last 3 to 4 years, and in particular for Roger for extending me the invitation. So this work is done in collaborators. The folks without attributions are my colleagues at Sandia. As it was mentioned, I'm an applied mathematician, but I'm not going to try not to give a talk I would give in a math department. In fact, I will not. Okay, so what is Predynamics? And by the way, I don't explain the origin of the name Predynamics, so let me do that first. Peri is the Greek word for far, so far dynamics. You'll understand more in a moment. And it was due to my colleague Stuart Silling, published a paper in 2000, and he had been doing a lot of computational mechanics where he was quite disconcerted with all the supplementary information you had to provide continuum theory to be able to model discontinuous deformation. In particular, he was interested in doing 3D material failure. And so he introduced a notion, he didn't introduce the notion of non-local model force, but he exploited it. And exploited it in a fundamentally new way, as I hope I will be able to explain. There's just some pictures to give you an idea of the type of fragmentation he's interested in, and also the type of fracture and cracking that he's interested in. So I guess I'll take a moment and say how I got involved in this, as I'd been doing work in, I'd started to do work in multiscale analysis, and all of a sudden I realized that my colleague in another building, he's now down the hall from me, actually had something that we could use. And so I've been working quite hard over the last few years to try and get a better understanding of what he's done, and to see if we can actually provide mathematical theory and mechanical, basic mechanical understanding of why this idea is very appealing. Okay, so a brief outline is I'm first going to give an extended introduction. I'll introduce the balance of linear momentum, the paradigmatic balance of linear momentum, and then I'll spend some time describing non-locality force, in particular what he means. Then I'll discuss some applications to motivate that this is not just strictly mathematical theory or mechanical theory. Then the second half of my talk, I'm going to discuss some further results that I've been involved with, that I guess I've been leading, which is actually starting to get very exciting now after about 3 years. I am, again, an applied mathematician, but I'm going to try and focus on trying to get across the main ideas and try and discuss what I think is the impact for practitioners. Please feel free to interrupt me with questions, or if I say something you don't quite understand. So anyway, the paradigmatic balance of linear momentum is right up here. We have inertia, and then it's the internal force density that's changed, and then we have the body force B. And this is an integral operator, and we're going to assume this kernel K is in units of force density per unit volume, and it represents the force that x prime exerts on x. So that picture, you can think of x and x prime as the ends of a spring, perhaps a nonlinear spring. They deform by u and u prime, and so now their distance, the vector between them, is given by x prime minus x plus u prime minus u. So k explains that force. In some extent, you could think of it in a very preliminary sense as a spring constant. So the material-specific behavior is in here. We're going to get into that more. And it turns out a very important property of this kernel is that it's antisymmetric. And this is a necessary and sufficient condition for the balance of linear momentum to hold. And I'll be using the following shorthand prime, so I don't have to write out all the variables, independent variables. Okay, so as I mentioned, in 2000, Stuart put out this theory, and there he assumed that the kernel K is parallel to the form bond, as you can see in the upper left-hand right there. He did consider volume-dependent strain energy term, so you can go on pairwise force interactions, but the force the force vectors still are collinear with the line between them. You actually need to go beyond that if you want to do interesting mechanics. And so he's now extended the theory in something he calls paradigmatic states, where he actually allows us. Now, almost everybody's heard of Newton's third law. It turns out that there's a distinction between the weak form and the strong form of Newton's third law. That's the strong form, the latter's the weak. And in the classical continuum theory, you really just have the strong form of Newton's third law. You can also derive the balance of linear momentum from Hamilton's principle, or you can consider a Lagrangian approach. I will not be discussing those during the remainder of my talk, but it's an important point to make. So Paradigmatics is an example of a generalized continua. Okay, these continua are not new. The first was due to the Coursera brothers in 1909, two Frenchmen, and probably more recently there's Eringen's model that he called micromorphic. You can classify generalized continua into three types. The first augments a displacement field with supplementary fields like rotations to provide information of fine-scale kinematics. You can augment a gradient to the displacement field with higher gradients. We'll get to that a little bit more in a moment. And then you can also consider an integral operator to average forces. And in particular, paradigmatics is of this last type. Okay, so let's say at a very intuitive level, what do we mean by local and non-local model of force? So the classical continuum theory, the force model is local because the force between the interior and the exterior of this cube is transmitted through the surface. That's the Cauchy hypothesis. And so in particular, material delta V and delta V prime separated by a finite distance then cannot exert forces on each other. Not directly. They would have to transmit the forces through the next cubes that they interact with, and so on and so on. Okay, so non-local model of force, if you want to draw a picture of that, the idea is that the exterior of the cube imparts force to the interior, and it's not just relegated to the surface. Okay, so something that I thought a lot about is to actually come up with a more basic understanding of the non-locality force, in particular the way paradigmatics does that. And it seems the way to start is by understanding the kinematics. So let's for a moment just review and discuss deformation. So I have a body omega and I have 2 points, x and x prime. There's a deformation, psi sub t, t just stands for time, and they displace by u prime and u respectively. So this is just 101. And so I can now relate that deformation to the displacements as in the top line right here. And then I'm going to define a quantity called phi of x prime comma x, and I'm going to define it to be the difference, the vector between. And you realize then I can relate things back to the deformation. Should I approve? No? Okay. All right. And it turns out that you can approximate that difference via the deformation gradient times the difference, right? So this is, many people forget this, but this is the assumption that's done in classical continuum theory, that the distance between 2 points that are deformed, you're going to approximate via this local approximation. Now, I mentioned higher gradient theories. You can obviously throw in the second derivative, third derivative, and so forth, okay? And so the deformation gradient is an intrinsic quantity at the heart of the classical theory, okay? So how does force arise? It arises through constitutive relationships, right? You map deformation to force density via that constitutive relationship. In a classic theory, I have the divergence of a stress, and for elastic materials, that's the divergence of the deformation gradient. You assume it's a function of the deformation gradient. If you're doing nonlinear elasticity or finite elasticity, it would be grad of phi transpose times grad of phi. Well, what is paradigmatics doing? Paradigmatics is actually using the actual deformation, and it maps that to the force density. So that's why you need an integral operator to map all of that deformation. So it's non-local because points x prime not equal to x are involved, which is distinct from the classical assumption because there everything can be described by what happens at the point x. So here we see that non-locality of force in paradynamics is a consequence of using the actual deformation in contrast to the deformation gradient. Okay, so that's simple enough, but this has far-reaching consequences. Okay, so Walter Knoll, the famous continuum mechanician, defined simple elastic materials to be ones that the stress at a point only depends upon the strain at that point. Okay, and an implicit assumption when you read Knoll and Truesdale's work, Knoll was a student of Truesdale, was that an assumption is that you always have a smooth deformation so that the deformation gradient adequately describes your kinematics. So why would you use the actual deformation? So as a mathematician, this is a big one for me. Minimal assumptions on the regularity of the displacement field. In fact, I'll give you some hint toward the end of my talk that what this actually gives rise to is that the space of admissible displacements, or that function space, actually allows discontinuous displacement fields. They don't have to be continuous, let alone differentiable. That has the effect of introducing a length scale. So this is the multiscale aspect. And also, it's quite now quite in vogue to consider using particle mechanics, something like molecular dynamics, to introduce a length scale or to get at finer scale motion. Well, this is the same sort of kinematic assumption that's made in particle mechanics. And this was one of the motivations for Stewart was to try and come up with a continuum version of molecular dynamics. Over the last year or two, we've realized that this is a nice way to understand things from kinematics. Okay, so multiscale mechanics, where's the length scale? So if I integrate that force density, that integral operator, I get back a force, and by using anti-symmetry of the kernel K, I can actually get this quantity right over here, so that what this term on the left here represents is the force that all the material outside of omega x within omega exerts on omega x. But typically what you find is that the forces don't extend infinitely far, that the horizon, so you will, force interaction is zero outside of some sphere, let's say h sub x. Okay, so that represents a max length scale for the non-locality force. So in contrast, the classical theory, because it relies on the deformation gradient, doesn't have a length scale. The horizon consists of a point because of the kinematic assumption of the deformation gradient. So let's continue here. And so now I want to start getting to some applications to give you an idea of what of these assumptions can give you. But let me give you a quick idea of how you would discretize this. A very simple way you would discretize this model is you break up your domain into, let's say, elements omega I, and then you can write things in the following form. You can go ahead and just introduce that decomposition for omega. Okay, and then the approximation would be one of quadrature. And a simple-minded quadrature scheme would be just represented at some points xi, where each of the x sub I is in some point within an omega I. Okay, so you got n sets of equations right here. And in general, they're nonlinear. We haven't made any assumption of a linearity. So you can show that this is a discontinuous Galerkin method where you're using piecewise constants, and it leads to meshless method because you just need these particles, right? At this level, all you need is these particles. The partition is just to make a link with the domain, okay? And what's very interesting is that these equations of motion now give rise to, let's say, data structures that are synonymous with molecular dynamics. Well, that are very evocative of molecular dynamics. So we thought about that in my former postdoc, Mike, who's now a staff member. I had him implement this within a molecular dynamics code. Sandia, Steve Plimpton, the third author, has a well-regarded public domain molecular dynamics code. So Mike worked hard, and he just got paradynamics implemented within this MD code. And so This gives you MD users a computational mechanics capability, and it also enables atomistic and continuum simulations.
Is that part of the current distribution of Young?
Yes, it is. And so to give you some now, I'm going to switch over to applications. And Stuart has his own code, a Fortran 90 code that he developed. So I'm going to, these were done with his code. Then I'm going to show you one that was done with the LAMPS implementation. But to give you some of the applications that were done is composites. This has been done with Boeing. They've been funding Stuart to do sorts of material simulations for the last 5 years. Have more to say about the composites in a moment. Florian Boberu is at University of Nebraska. He got very interested in this, so he's been doing a lot of work with Stuart. Here's a dynamic fraction of polycrystal, oscillatory crack oath, and I'm going to get into some more details in a moment, just at a high level, some of the range of applications that they're doing. And for a recent review that was just published last year, I presented this paper at a SIDAC meeting that I was invited to give a talk at. And so we kind of surveyed everything. It's a 15-page introduction, and I think I mentioned to Roger that Stuart and I are preparing a paper, an extended review for advances in mechanics. Okay, and then with respect to composites, if you want to find more of the details, Stuart and his Boeing collaborators, the first three are Boeing collaborators, actually published this journal in JAE last year, and they were awarded, the paper was the best paper of the year for a journal of aerospace engineering. So those are some, and you can find about those 4 applications I said in the review article. In particular, you can learn more about the composite work in here. Okay, so now what I want to do is just to give you a context in a specific material model. I want to describe a certain application that we did with the LAMPS implementation of Predynamics. So this is, and this was work done by Mike and Florian. They were kind enough to share some view graphs with me. So soda lime glass plates, it's macroscopic objects, something that you can hold in your hand. Okay, so the idea is that you're going to have a defect at the top, like a notch. Okay, and then you're going to apply a load slowly at the end, and there's going to be a fully dynamic simulation. And then you want to see how whether a crack occurs and how it grows. Okay, so the finest level of discretization that Mike ran involved 82 million particles, or 82 million elements, if you will. It took 50 microseconds, 20,000 time steps. Okay. This is 6 hours of computation time on a huge machine at Lawrence Livermore that I'll give you some more details on. So he got awarded some time to run this on that machine. Okay, and so this problem comes from the following paper where where physical experiments were done, but nobody's been able to simulate this. And I should be careful to say it's not clear to me what sort of concerted effort has been made to do computational simulation of this, but Mike and Florian thought this was a very interesting problem, and there's a still that we did with, that Mike and Florian did with lamps on the right, and at least it says that you seem to have matched a profile, and so hopefully these movies will work. So right here, you can barely see a crack right here. So there's a thickness here, right? This is a 3D simulation, so essentially some bonds were broken, right? Think of this picture of springs. So some bonds were broken, so there's no force interaction along a small diameter down the middle, and that we're going to apply a load to the side and see what happens. Okay, so now you start to pull, and the crack starts to grow. It speeds up, it bifurcates into 2, and then it finishes. Okay, so
is the background mesh an actual mesh?
No, this is an aliasing effect due to the graphics. So this is there's no intent to put a background mesh. We don't really have one. It's a meshless method. So what happens is, and this is what you see in the experiments, is that the crack hits a critical velocity, and then it bifurcates into 2. Okay, so it's very interesting that at least the qualitative behavior of that was captured.
So what's the horizon in this problem?
I think it would amount to basically 4 neighbors.
how did you select the kernel?
I'm going to get to that.
Okay.
Yes. This thing has a mind of its own, so let me see if I can show this one. All right, so this one, if we make a, okay. So let me, all right, well, with this one, which shows we plotted the strain, they plotted the strain energy density as a okay, here we go. So now you plot the strain energy density all over, and so when it starts back up again, you'll see that the way that strain energy density starts to propagate. So in some sense, the stress waves, okay, they hit that notch at the top, and then a crack starts to grow, and then the largest intensities is right along the red where the crack branch is growing. Okay, so that gives you some idea of the mechanism. Let me go forward. Okay, so now the material model. So this is the point I want to make, is that this was actually very straightforward to do. So the material model was a nonlinear model. It's called a PMB model. It's due to it was introduced in a paper by Stewart and a technical fellow at Boeing, one of his collaborators. And so essentially that kernel is essentially a stretch, right? The outside of the C, that's a dimensionless quantity, and it represents the stretch undergone by the force between two particles. And then this is a unit vector, so you stretch something in that direction, okay? And then how do you break bonds, right? How do you cause damage? Well, when they stretch enough beyond a critical stretch S star, okay, then all of a sudden you set that equal to 0, okay? And just to make a point that critical stretch S star can be determined from the energy release rate, which you can determine from experiments, okay? So the same equations, the same material model was applied everywhere, and that crack and the branching happened all outs unknown. So it's not a very complicated process, and this was fully dynamic. This was not a sequence of load steps, okay? So no one is claiming that this simulation matches experiments perfectly. This is preliminary work, but certainly with not much effort, the qualitative aspects were very much the same. This sort of scheme where you introduce a fracture by breaking of bonds is what you would do in something like molecular dynamics. Okay.
Richard, are you matching the velocity, the wave velocities in these problems?
I think they're still determining that. This experimental paper, though it was written in a time where they weren't necessarily concerned with providing enough information and data so that somebody could match a computational method. So they're trying to work that out. So my whole purpose of this was to show how simple it is to do damage in 3D, right? This is very simple, and it can be calculated from the energy release rate.
But one could choose a different model, right?
Absolutely. Yeah. This is the simplest nonlinear model, right? This is it's got a geometric nonlinearity, right? So yes, certainly there are other, this is not the only material model that's available in Predynamics.
It looks like you're just using a windowing function that's just, if I'm outside of here, 0, and if I'm inside, then whatever this is.
Yeah.
There's no attempt to taper it down in a smooth way.
No. These same equations hold everywhere. So maybe I'll make a few more comments. So the idea is a very natural one. I have all these springs, right? So from a particular point X, I have an uncountable number of springs. When I discretize, I have a finite number of springs, but there's overlapping springs, right? Okay. So then what happens is one of the springs gets stretched far enough, right? It breaks. So that pushes that the remainder of half the springs have to absorb the load. Okay, then basically enough of the springs break, and that's where you have damage, and then it accelerates things. But the path of this was determined all by the model. No supplementary information was added other than this critical stretch S star. Okay. Anyway, just some computational details. This was done. This is the big machine. It was done at Lawrence Livermore. And this plot gives you some very statistics. Mike was very interested to see what was a parallel scalability, and he was getting excellent parallel scalability. But that's what you would expect from something you could implement within a molecular dynamic code. Okay? And that was the reason why we thought to put it in this molecular dynamics code, because that code is ported to every big machine, to many big machines. So anyway. All right, so I'm about halfway through here. Just want to put into perspective where I'm at. I try to give you an introduction, discuss this very important non-locality force, and discuss some applications, and went into some modest detail on one particular application, give you an idea of how all this works. So now I'm going to discuss some, I guess, more fundamental work, in particular non-local stress, some statistical mechanics, connections, coupling with classical elasticity, and then what we're working on right now, some variational analysis. Okay, so you could you can define such a stress tensor. Okay, so I think you can see from this picture what alpha and beta represent, dimensional distances from the point x. Okay, S sub m represents a solid angle on a sphere, and if you know, admittedly at this point that comes from the sky. If you actually take the divergence of that tensor, you actually recover this non-local right-hand side. And what this picture is trying to evoke is that the stress right here represents a sum of forces through the point x, whereas in the classical theory it's point-wise. This is some average. You can actually derive this tensor from a force balance equation. Okay, I have an animation for that, but I think there's enough other stuff I decided not to include it, but I'm happy to explain that to people. There's also an alternate derivation that we've become aware of, and I'll get to that in a moment. And so,
Are you symmetric?
well, this is the way Stewart posed the theory was in a Lagrangian frame. So this would represent a Piola, would be an analog of Piola-Kirchhoff. Okay, but you can consider an Eulerian frame, and then you can derive a similar sort of tensor, and that will be you do have a Cauchy stress. It's not always symmetric, and it's got to do with the fact that we do allow a peridynamic model where we satisfy the weak form of Newton's third law. So that, in a sense, introduces some coupling mechanisms. So you can actually get a non-symmetric Cauchy stress.
So you have micropolar right there.
Exactly, without having to introduce rotations. That's right. So that would be actually a good point. That's a good question. That's a good point to bring up. Is we seem to be able to get these sorts of polar effects without introducing these auxiliary fields. So it's a simplified. It's let's say a nicer model in that sense. You can find the details of this in a paper that Stewart and I published in JMPS in 2007. Okay, and it turns out that we were also able to actually derive a non-local Gauss's or divergence theorem, right? So I just showed you that the divergence of nu is equal to that inner integral. Well, I can obviously integrate both of those sides with respect to some omega x, where x is some point in the domain and omega is some region about that point. So omega x is a subset of omega. And then, well, certainly Gauss's theorem tells me, well, that's equal to nu dot n over here across the surface. But then I can play around with that right-hand side and get this. So that now tells me that I can actually talk about a Gauss's theorem, right? Because that means the two right-hand sides are equal without recourse to the divergence of a stress tensor. So it's very interesting. I get the same behavior. I get the same sort of ideas without having to talk about surfaces, unit normals, and so forth. And this turns out to be very important for the emerging mathematical theory that I'll just touch on at the end of my talk here. So, and traction. So what does traction here seem to represent? Again, I had broke this down for you, but let me explain it again. It represents the force that the material external to omega x exerts on the material omega x, right? So that's traction. So now it's not just relegated to what happens to the surface, but everything on both sides of the surface. Okay, so compatibility and some conservation of momentum. So again, I write down that equation. That's equal to the difference of the applied force and the inertia, right? Well, if I choose to integrate across the volume omega, well, omega, take out omega, 0. So I get the following compatibility equation on a body force, and then I get something that's, you get the conservation theorem that linear momentum is conserved in absence of external forces if the integral of B were equal to 0. And this statement here is nothing more than the sum of internal forces is equal to 0. Okay? I'm not going to go into it, but you can also consider balance of angular momentum. And a sufficient condition for balance of angular momentum is that the Cauchy stress is symmetric. But you can have balance of angular momentum without, even when you have a non-symmetric Cauchy stress. Okay. So it turns out that as we were revising this paper, I came across this paper by Walter Knoll, buried in a journal. And I translated with a German postdoc at Sandia, and it's going to be published in the Journal of Elasticity. And it turns out that the peridynamic stress we derived was essentially equivalent. We use a different coordinate system, but equivalent to one that Walter derived. But it was very interesting. He derived it in a paper in which the title of that paper is Deriving the Fundamental Equations of Continuum Thermodynamics from Statistical Mechanics. Okay. And it turns out that he provides two lemmas where if the integrand G is antisymmetric, and I remind you of what that means, then he came up with a closed form expression for S such that divergence of S is equal to the integral. And that should be, instead of B, should be omega. Okay? And so essentially, we reproduced his results without knowing. There is some minor differences between what we did and he did, but certainly not enough to say that we just basically reproduced his results. And fortunately, we were able to point out this in our paper. So he used this because he wanted to determine a stress tensor S of V that was equal to V2, and here V2 is this. And I want to try and motivate this a little bit, because this has become very important. So this is an interatomic potential. You take the derivative of it, so you get a force. This represents an ensemble average in phase space that I'll briefly describe in a moment. And these are two particles, but this is an integral operator, and I'm integrating across dy, and r here is the distance between x and y. And when I saw that, it actually took me a few months to really appreciate what was going on. And what we ended up realizing going on, Mark and I were able to write a paper. We're currently revising it for PRE, where we were actually able to generalize the approach due to Walter. And Walter's approach was an exact derivation due to two theoretical chemists from 1950. This is a seminal paper of how you derive continuum balances as expectation and phase space. Walter substantially improved the mathematics of what they did, and then Mark and I were able to generalize beyond just considering parapotentials to multi-body potentials, but in particular we were able to show that peridynamic state theory was actually what's suggested by this expectation in phase space. And so this is very interesting. It says that this internal force density given by an integral operator is intrinsic. The divergence of the stress tensor, is something that you derived in a post-processing step, right? So what's more intrinsic, the internal force density or the stress? That's kind of a philosophical argument, but we were very happy to show that what Stewart phenomenologically posed over the last few years has a basis in statistical mechanics. Okay, so the basic idea of how you would generate those balance equations. So you would express density, mass, momentum, and force as expected values in phase space. Phase space is a product probability space of positions, momenta associated with a collection of atoms or particles. Then you use Liouville's equation and divergence theorem to compute the rate of change of this expectation. Liouville's equation is a conservation law on how phase space density is conserved. And then careful manipulation results in the local balances of massive linear momentum. And again, I've already made this point, but that's just to emphasize it. It shows that when you do this, force density is a non-local quantity. So the local assumption of contact forces actually is a subsequent approximation. And I'm going to get more to that in a moment. Okay, so kind of maybe a picture to put things together. There's a paradigmatic equation of motion. Here's particle mechanics. This works at a certain length scale in angstrom. That's the typical engineering scale. That's the classical equation. So we've somehow related this and this. Shows that this arises a statistical averaging of this. Okay. And now what I want to do is connect the classical theory with the paradigmatic theory. So I just remind you divergence of a stress is equal to this integral operator. And we motivated that it uses the actual deformation phi, and the relationship to the deformation gradient is that the deformation is an approximation, the best local linear approximation to that deformation. Okay, and then in 2008, Stuart and I published a paper where we were actually able to show that the divergence of this nu is equal to the divergence of a nu. This should have a tilde here or something. It's not the same nu. That's a typo. Is a divergence of a Piola-Kirchhoff stress plus a term that's related to the radius of that horizon. If you consider that, you can go ahead and assume that that's a sphere, so the radius of that sphere. Okay, so this is an asymptotic expression. So for small delta, you have this approximation. So this theory is not counter to that. It's an enhancement, and again, it arises from the kinematics, right? Now that you see that this is an approximation to this, it's not surprising that you should be able to come up with some sort of decomposition. And this again is for the nonlinear model. We didn't make any assumption of linearity to get this result. Okay, so what's this have to say about multiscale materials modeling? So the paradigmatic and force density augments the classical internal force density, and in particular it allows discontinuous deformation. We don't have singularities because deformation is discontinuous. I conjecture that this forms a rational basis for the development of a coupling between a classical theory and paradigmatics. That should just be one. Okay, so a very simple idea is to use a classical theory in regions where you have smooth deformation, and then use paradigmatics otherwise. But in order to get a viable materials model that you could put into code, I mean, there's several things to understand, paramount of which would be the notion of boundary conditions, spaces of admissible functions, the price characterization of this approximation between paradigmatics and classical elasticity. So how I'm going to end my talk is just to give you an idea of how you can do this. And we're going to start with the linear theory, right? And so one can pose a following variational equation for an equilibrium problem. Okay, so you want to find the displacement u in some space that satisfies this variational equation for all v in the same space. And here the space nu sub naught is where this energy, this is an actual energy, is less than infinity, and v is equal to 0 on this boundary. So because of non-locality, you can't actually talk about restricting a function to a surface. You have to actually restrict it to a strip. So this very much corresponds to a homogeneous Dirichlet boundary condition, okay? And so what is this object over here, okay? All right, so turns out that if we assume u and v are scalars, okay, and mu is a scalar, okay, then this corresponds to non-local steady-state diffusion, for example, heating. So you can apply these non-local ideas to non-local transport, in particular to heating, okay? And this problem corresponds to homogeneous non-local Dirichlet boundary value problems. You can extend it to non-homogeneous, and you can consider Neumann non-local boundary value problems. We were able to derive non-local Green's identities, and this is all in a paper that Max Gunsberger, one of my collaborators at FSU, and I have submitted for publication, okay?
Excuse me, can you go over this kind of artificial boundary conditions here?
Can I go over it?
I don't understand the concept.
Okay, so if I was working with the classical theory, right, one set of conditions I can use to solve that problem is to suppose that, for example, if mu was playing the role of temperature, that the temperature is 0 along the boundary, right? The effect of non-locality is such that you can't talk about a trace operator. You can't just sample a function along a manifold.
You need to introduce a gradient of temperature.
No, if you introduce a gradient of temperature, that means you're making an assumption that the temperature field is smooth, and I want to get away from that.
I see.
Okay? So exactly, because I'm not making an assumption of a local linear approximation to gradient, that means the cost of that is that I now have to talk about boundary conditions along some layer. Okay?
So not only you introduce values of the boundaries, but you introduce higher orders, whatever field at the boundary.
No, I'm not introducing any higher order orders.
You let them,
Yes, it's just u prime minus u, and I test against v prime. I mean, if you think about it, u prime minus u is a difference, right? So that's basically what you want.
Are you saying that you're setting the temperature within that band?
Exactly.
If to be a uniform temperature?
No, you could. It could be a function.
Some function.
Yeah, to non-homogeneous Dirichlet. Yeah. So you could let that be a temperature field. Okay. This is an example of steady-state non-local diffusion. If you Google on non-local diffusion, there's stuff out there on that. In fact, from a probabilistic sense, this corresponds to a variational counterpart of what's called the master equation if you look at stochastic processes. So it's not like the essential ideas are coming out of nowhere. What we did was, it turns out nobody ever talked about boundary conditions and a variational analysis and get all the Green's identities. So we can get you can get Green's identities without having to talk about divergences or gradients. That's a very powerful thing.
So you're allowing for jumps. That's what.
Exactly. Exactly. Yeah.
And Green's identities with jumps.
Excuse me?
So you have Green's identities with jumps replacing.
Yeah. Yeah. So let's discuss that a little bit. To make everybody feel better, right? You can actually talk about conditions under which this thing converges to that term. So you have a tensor D, and then you have grad U, oh, that shouldn't be a dV, that should be just, no, it's a grad V, okay? And then you can talk about this space approaching the space that the mathematicians work on, right? So this is the space of all square integral functions, functions whose gradients are square integrable, and that have an essential boundary condition of 0 along the boundary, right? That's all that we mean. So you can recover standard weak formulation given sufficient conditions. Work that we're doing with Chung Du at Penn State is to actually show that in a general setting, the space nu, V sub 0, is equivalent to a fractional Sobolev space, okay? And it's depending upon mu is the big ticket right here. That's in the linear theory, that's the thing that really changes things, that the space of admissible variations contains discontinuous functions if mu is not singular, right? So the way you recover, the way you get this approximation is you're essentially going to assume that mu is an approximation to Dirac delta. So you're localizing things, okay? So if you stop and think about it, you would think, well, yeah, that has to be the case. Actually showing it is something else altogether, okay? So again, this is this work in extension to linear paradynamics, where we actually look at where V and U are vectors, is that we're working on right off the bat.
Rich, the fractional Sobolev space, does this suggest that you may be governed by a fractional differential equation?
Yes, thank you. That's a good cue. it turns out that the way to understand a fractional Sobolev space is just like in this space, the Laplacian defines the inner product, right? And this space, what defines the inner product is a fractional Laplacian, okay? And people have known that fractional Laplacians are good for damage, but how do you discretize a fractional Laplacian? Nobody knows how to do that. It's a pseudo-differential operator. What we're able to show is that this integral operator is energy equivalent to that fractional Laplacian. And as I've already motivated to you, it's not hard to discretize this. So once again, no ideas are really new. You're just showing that something's related.
Long-range interactions in fluids have always been described with fractions.
Yeah.
So,
Yeah. But here we can talk about fractional Laplacians without, you know, in a very nice looking model.
I'm trying to do that here.
Yeah. And then I think, oh, okay. So I think this is my last view graphs, okay? So some implications here is that what this analysis is also telling you is that non-local second order problems, this problem is a non-local second order problem, doesn't smooth the data, okay? So in a standard case, in a classical case, your solution gains two derivatives over the data, all right? Laplacian of u equal f, okay? This shows that you may gain, if you allow me, a fraction of a derivative, okay? And so now multiscale coupling reduces to synthesizing function spaces, and that I claim can be made precise. So naturally, you have a basis. I'm on a stronger footing for making a claim that we have the start of understanding how to couple things, because I think I've motivated that you can use Predynamics for a lot of the things that Continuum people are looking to for molecular dynamics. And then a lot of this work, because Max, my collaborator, is an expert in the math theory of fine elements, is we're laying the foundation for a conforming fine element method that is well posed for multiscale materials modeling. So, and then I think just to give you an idea, to go over everything we talked about. Thank you very much for your time.
We're going to take a few questions from the floor, and maybe we would take also some questions from the audience. If we can, the audience, we do have audience over the internet, and you have to raise your hand through a little knob on your webinar. And but first, we will take questions from the audience. Okay, so please monitor if you have questions from the web. Any questions? Yes.
So it seems like you've taken force to be the sort of primary quantity, and in some other, in like Lagrangian mechanics, for example, you have energy as the primary quantity, and gradients of energy gives you force. Have you worked with sort of energetic-based theories of this, or do you have a correspondence that could?
So you can derive the Predynamic balance of linear momentum from you can pose a Lagrangian or a Hamiltonian and derive the balance of linear momentum. But this essentially is a principle of virtual work right here, right? In particular, if V were a velocity field, right? I mean, I could restrict it to be a displacement. This is the principle of virtual work. And that was the whole idea of getting these Green's identities, equivalent of identities. And certainly to do the mathematical analysis, you need exactly, you know, you need to base things on a principle of virtual work. So is that what you mean by energetic? Yeah. There is yet another issue, which is the other thing that we're working out, Stuart and I, and primarily Stuart and I, is we're actually coming up with an energy equation, because in some sense I'm saying I have non-local heating, I have a balance of linear momentum, and I can put everything together through the first law of thermodynamics. So we actually are in the midst of working out, finishing that off, and also considering an entropy inequality, so we can determine restrictions on the constitutive relationships so that we don't violate thermodynamics. The non-locality is a little bit more subtle when you start looking at the first and second law of thermodynamics. Yeah.
There is a question I have. Have you looked at the propagations of waves within these materials? Are you dispersive? What are your basically attenuations? And the scary part is, I hope you don't get negative attenuation.
No, no. Well, let me tell you what I know, okay? And then hopefully it answers your question. So if you study the dispersion relationships here, what you find is, for example, for this problem, if mu is like a delta function, you'll find that the dispersion relationships are linear, just like it would be for linear theory. However, what you can actually show is that for actually smoother mu, the dispersion relationships actually settle down. So it actually does, right at the continuum level, does a much better job of matching the dispersion relationships associated with particle mechanics than the classical theory. There is always a finite speed of propagation associated. For material stability, you see that you have to have that the speed of the waves has to be real valued, and there's a finite speed of propagation for the waves.
Good, that's a good fact.
Yeah, yeah, yeah.
Roger, you have a question?
Yeah, can't you describe the interplay between the scales using distribution theory, perhaps? Or generalized functions? Or does this revert to that?
That's exactly what we're doing, yeah. Yeah, that's kind of buried. The way you show this, okay. The way we can also show that these equations are well posed. In other words, there exists a unique solution, and that the data, the solution depends continuously on the data. Okay, so one of the reasons we've worked so hard to get non-local equivalents of the Gauss's theorem and then the Green's identities without having to talk about div and grad, right, okay, is so that we could get all of this. Okay, so it's there.
One other question. You said you jump by a fraction of the derivative at some point. Now, the magnitude of that fraction, does it depend on the horizon or on the density of forces?
So you're talking about this statement, right?
Yes.
Okay.
When you gain a fraction, I mean, how much you gain, does it depend on how many neighbors you care about?
The answer is that it depends upon mu. And so mu, you can think of mu as being of compact supports.
Okay, so how much is the density of forces?
It not only depends upon whether the range of its compact support, but its regularity. Okay.
Is it mostly the regularity, you think?
It's it's primarily the regularity.
From K, right?
No, mu is a material parameter, right? So mu of x prime comma x.
But the kernel K.
Oh, this is K. Well, this is actually V cross K. So I'll show. But K is actually K is mu prime minus mu times that.
Yes.
Okay, that is K.
Yeah.
Okay, so this is an example of a linear K. Yeah, but it's really the regularity. If the first moment of mu, if the integral over omega of mu is finite, okay, then you're not even going to gain a fraction of a derivative. The way you gain even a fraction of a derivative is by that has to start approaching a singular sort of a function, and that's interesting to bring out because here's this is temperature, but you can talk about the mechanical model also. You can actually talk about elastic phenomena in which the solution is no smoother than the data. They live in the same space.
Solution no smoother. Okay.
Yeah. So this is.
But for particles, that should
yeah,
be
and if you think about this hierarchy of scales of these spaces, as you minimize over a larger and larger space, what can happen with the associated energy given the same data? It can be smaller. And that's actually a very interesting physical implication, is that you can actually get to an elastic state that has smaller energy. So in some sense, it might be saying for certain problems and certain data, nature prefers the smallest energy, so you need that discontinuity.
One last question associated with the same idea. Now that you have some knob that you can tweak in order to increase derivatives,
Yeah.
could you go from first derivative to second derivative to fourth derivative by tweaking the knob quite a bit? And this will take you from a bar to a beam to a plate to, you know.
That
you seem to have the mathematical structure to do that.
I suspect you could. I hadn't thought about that. Yeah. Because this is kind of like first base, right? If we can't get all this worked out,
Yeah.
there's no reason to even address those questions. Okay.
We should. One quick question. The mu is something that's compact support, right? And so it has some.
It can be, doesn't have to be, but you can choose it to be.
Let's choose it to be. So
Okay.
then it has some scale that's inherent in it.
Mm-hmm.
And is there some way that we can decide what sort of the best scale is for a given problem? Perhaps by knowing something about the size of the physics at the microscale.
Yes, that's an excellent question. So there's two ways to do this. One way would be to look at like theories in heterogeneous media and microstructure. They'll often talk about a paired density, so you could get mu that way. The other way to do it, which is actually inverse problems, is that often what people have is data on the dispersion relationships of their material. So now is given those dispersion relationships, solve an inverse problem to get the mu, because the regularity of mu is directly associated to the dispersion relationships.
Well, I'm looking at the clock. I have also many more questions, but in view of the time, we're going to have to close the seminar. But before we do that, I think we should thank our speaker again. Thank you.